A dam can hold back billions of gallons of water, generate electricity for entire regions, protect cities from floods, and keep farmland alive. But the same structure can also become one of the most dangerous pieces of infrastructure on Earth. A failing spillway, unstable ground, extreme rainfall, or one mechanical failure can transform a wall of concrete and earth into the starting point of a catastrophe. And history has already shown us what happens when that goes wrong. Today, we are counting down 9 of the most dangerous and controversial dams in the world, from structures that forced emergency evacuations to one dam disaster that became one of the deadliest engineering failures ever recorded. And number 1 proves that sometimes the most frightening danger is not the size of the dam. It is what can happen inside it. Before we begin, tell us in the comments, would you ever feel comfortable living directly downstream from a massive dam? Number 9. Morning Glory Spillway, United States. At first glance, it looks less like part of a dam and more like a hole leading straight into the earth. But this giant circular opening in California was deliberately built to swallow water. Picture the calm blue surface of Lake Berryessa. Near the edge of the reservoir, the water suddenly curves downward into an enormous circular opening. From above, it resembles a giant drain in the middle of a lake. When reservoir levels become high enough, water begins pouring over the rim and spiraling downward into the structure. The Morning Glory Spillway is connected to Monticello Dam in California. It is designed to control excess water when Lake Berryessa rises above a certain level. According to the source material, once the water level rises above approximately 440 feet, water can begin flowing into the spillway before being carried through a pipe and released into Puda Creek below. The design is unusual because it works differently from the more familiar spillways built along the side of a dam. Instead, this one looks almost like a giant engineered sinkhole. The spillway does not constantly look this dramatic. Conditions have to be right. That means the famous image of water disappearing into the giant circular opening can only be seen when reservoir levels are sufficiently high, but what looks spectacular from a distance can be deadly up close. The source describes a fatal incident in 1997 involving a swimmer who was caught in the current and pulled into the structure. Swimming near the spillway is prohibited. What makes this structure important is that it shows how even systems designed for safety can themselves become dangerous environments. A spillway exists to protect a reservoir and dam from excessive water. Yet when enormous volumes of moving water are involved, the safety system becomes something humans must respect from a distance. And while this giant drain looks frightening, the next dam faced a threat far more difficult to see. Because in Iraq, engineers have spent years fighting an enemy hidden directly beneath the dam itself. Imagine building one of the country's most important dams on ground that can slowly dissolve when exposed to water. That is the challenge beneath Mosul Dam. The structure stretches across the river like a massive barrier cutting through a dry landscape. Behind it sits an enormous body of stored water. But the real story is underground. Beneath the dam are layers containing gypsum, a material that can dissolve when water reaches it. Mosul Dam is the largest dam of its kind in Iraq, according to the source. It stands approximately 371 feet tall and stretches about 2.1 miles. It also provides electricity to residents of Mosul. The problem is its foundation. Because part of the geology beneath the dam includes soluble material, cavities and weaknesses can develop. That creates a permanent maintenance challenge. Engineers cannot simply finish the dam and walk away. They must continue injecting grout into the foundation to fill spaces and reduce the risk created by dissolving material. The scale of that maintenance is extraordinary. The source states that since the dam's completion in 1986, more than 50,000 tons of material had been injected into the structure. It also describes machines continuously pumping grout into the dam base. In other words, the struggle to stabilize the foundation is not a temporary repair. It is part of the dam's ongoing existence. The same source also reports that multiple sinkholes developed in areas downstream and east of the dam over the years. This is not simply an engineering curiosity. Millions of people depend on major dams for electricity, water management, and economic stability. That makes continuous maintenance a matter of public safety. The terrifying part is that a dam may look completely solid from the surface while important changes are happening underground. But unstable geology is only one way a dam can become dangerous. Sometimes the threat arrives from the sky in the form of a storm powerful enough to overwhelm an entire reservoir system. And that is exactly what happened in Puerto Rico. For almost a century, Guajataka Dam served local communities. Then Hurricane Maria arrived. Within hours, tens of thousands of people faced the possibility of catastrophic flooding. Imagine dark storm clouds covering Puerto Rico. Rain pounds the landscape. Reservoir levels rise. Roads disappear beneath water. Then emergency warnings begin spreading through communities downstream. A dam that had stood for decades is suddenly being treated as an immediate threat. Guajataka Dam is an earthen dam used for irrigation and potable water. According to the source, construction began in 1928. The reservoir has supported surrounding communities and agriculture for generations. But on September 22, 2017, after Hurricane Maria devastated Puerto Rico, operators reported problems involving the spillway. Officials feared conditions could become severe enough to threaten communities downstream. The source states that around 70,000 residents in flood-prone areas needed to evacuate. The reservoir was holding an enormous volume of water. Emergency authorities were dealing not only with hurricane destruction, but also with the possibility that the water management system itself could worsen the disaster. The impact did not end when the immediate emergency passed. Repairs began later that year. At the same time, residents and farmers who depended on reservoir water faced restrictions and shortages. That is the difficult contradiction of dam infrastructure. Communities can depend on a dam for survival. But when the structure is damaged, those same communities may suddenly become vulnerable because of it. Guajataka survived the crisis. But at our next location, engineers made a decision during another historic storm that deliberately sent water into thousands of properties. Next, we travel to Houston, Texas, during Hurricane Harvey. Sometimes the terrifying decision is not whether to release water. It is choosing who gets flooded when there is no perfect option left. Houston is buried beneath relentless rain. Freeways resemble rivers. Neighborhoods disappear beneath brown floodwater. Behind Addicks Dam, water continues rising against a long earthen barrier. Engineers watch reservoir levels climb. Addicks Reservoir and Addicks Dam work together with Barker Reservoir to reduce flooding along Buffalo Bayou in Houston. The source states that the U.S. Army Corps of Engineers completed Addicks Dam and its outlet facility in 1948. The earthen structure extends for tens of thousands of feet. Over time, however, concerns developed around the condition of the dam. The source reports that in 2009, the structure was categorized as extremely high risk and critically near failure. Then came Hurricane Harvey in 2017. The dam did not collapse, but reservoir water rose to dangerous levels. Engineers began releasing enormous quantities of water in order to reduce pressure and protect the structure. According to the source, water was released at a rate reaching millions of gallons per minute. The result was devastating. Thousands of homes and businesses upstream and downstream were flooded. Some properties that had remained dry during the storm were inundated after controlled releases began. This event shows how flood control infrastructure creates extremely difficult trade-offs. Holding too much water can threaten a dam. Releasing water can flood communities. Engineers may find themselves choosing between two dangerous outcomes while a disaster is already underway. For residents, that distinction hardly matters when water enters the house. But the next dam reveals a different kind of risk. Not a hurricane, not unstable soil. A structure so enormous that its social and environmental consequences were measured in millions of people. That takes us to China's Three Gorges Dam. Some dams are large. Three Gorges is on another scale entirely. Its construction reshaped a river, transformed communities, and created one of the world's most powerful hydroelectric projects. Some dams are large. Three Gorges is on another scale entirely. Its construction reshaped a river, transformed communities, and created one of the world's most powerful hydroelectric projects. The Yangtze River meets a massive wall of concrete. Turbines operate deep inside the structure. Ships move through engineered passages. Behind the dam stretches a reservoir so large that entire landscapes were changed by its creation. The source describes Three Gorges Dam as the largest hydroelectric dam in the world by installed generating capacity at approximately 22.5 gigawatts. Construction required tens of thousands of workers and took years to complete. The project was conceived long before construction began, with the idea dating back to the early 20th century. When finally built, it became a symbol of modern Chinese engineering. It produces enormous amounts of renewable electricity. According to the source, its output can replace the need to burn vast quantities of coal. The dam's scale is difficult to imagine. The source compares the amount of steel used in construction to dozens of Eiffel Towers, but the human cost was also enormous. Approximately 1.3 million people were displaced during the project, according to the source. Historic sites were affected. Construction workers also lost their lives. Three Gorges represents one of the biggest questions surrounding mega projects. How much change is acceptable in exchange for energy, flood control, and development? For millions of electricity users, the dam represents power. For displaced families, it represented the loss of homes and communities. For the river ecosystem, the consequences continue through changes to water flow, fish populations, sediment, and pollution patterns described in the source. But our next dam shows that even a structure much smaller than Three Gorges can trigger the evacuation of an entire region when one critical component begins to fail. In 2017, more than 180,000 people were told to leave the area below Oroville Dam. Oroville Dam itself did not collapse. The terrifying problem was what happened next to it. Heavy rain fills California's reservoir. Water pours across concrete. Then the spillway begins breaking apart. Huge sections of the surface erode away as torrents of water tear into the ground below. Helicopters fly overhead. Roads fill with evacuating residents. Oroville Dam is an earth-filled embankment dam on the Feather River in California. At around 770 feet high, the source identifies it as the tallest dam in the United States. It plays several major roles, including water storage, hydroelectric generation, and flood control. Behind it lies Lake Oroville, one of California's largest reservoirs. In 2017, after intense rainfall, damage developed in the main spillway. Conditions later created serious concerns around the emergency spillway as well. The emergency became serious enough that more than 180,000 people living downstream were ordered to evacuate. That number alone demonstrates the scale of risk associated with major dams. The source also describes enormous quantities of erosion debris entering the channel below the dam. The damage interfered with normal operations and required major repairs. The total cost reached hundreds of millions of dollars. For residents downstream, this was not an abstract engineering issue. People had to leave homes, gather family members, sit in evacuation traffic, and wait to discover whether they would have anything to return to. Oroville also provides a powerful lesson in dam safety. The main wall is only one part of the system. Spillways, channels, gates, turbines, and foundations can all become critical points of failure. And yet, even Oroville's enormous evacuation pales beside what happened when our next dam actually failed. In 1975, a storm in China created a disaster almost impossible to comprehend. This was not a near miss. The dam broke, and the wall of water that followed became one of the deadliest dam disasters in history. Rain falls for days across China's Henan province. Rivers swell. Reservoirs rise beyond their limits. Then the dam gives way. A violent surge of water tears downstream at frightening speed, destroying nearly everything in its path. Banqiao Dam was built in Henan province in the 1950s. According to the source, it had been designed to withstand an extremely rare flood event. But in 1975, Typhoon Nina produced rainfall far beyond what the system could safely manage. The source describes approximately 3 days of extraordinary rain. The resulting floods exceeded the conditions the dam had been designed to withstand. Eventually, Banqiao failed. The source describes the released water moving at around 30 miles per hour, reaching heights of approximately 33 feet and spreading across an enormous area. A downstream town was rapidly devastated. Thousands died immediately. But the disaster did not end with the first flood wave. The source states that approximately 26,000 people died directly from flooding, while many more later died because of disease and contaminated water. The total human toll described in the source is staggering. One of the most frightening details is that this occurred before modern emergency warning systems were widely available in the region. Residents downstream had limited time and limited information. Many had no realistic opportunity to escape. Banqiao became a reminder that infrastructure designed to protect communities can create catastrophic consequences when an event exceeds assumptions used in its design. But the next dam did not need to collapse to kill dozens of people. The disaster happened inside the power station itself, and the warning signs were mechanical. Kariba Dam created electricity for 2 nations, but its construction also drowned landscapes, displaced communities, and forced an enormous wildlife rescue operation. The Zambezi River narrows through Kariba Gorge. Across it rises a huge curved concrete wall. Behind the dam sits a vast reservoir stretching toward the horizon. What appears today as a permanent lake was once inhabited land. Construction of Kariba Dam began in 1956 and was completed several years later. The concrete arch rises approximately 128 meters and extends hundreds of meters across the gorge. The project produces hydroelectricity shared between Zambia and Zimbabwe. Its electricity became especially important to regional industry. But building the dam fundamentally transformed the surrounding landscape. The source states that tens of thousands of indigenous people were displaced by the creation of the reservoir. As rising water covered former habitat, an enormous wildlife rescue effort known as Operation Noah was launched. Animals trapped by the expanding lake had to be moved. The image is extraordinary. Humans had changed the river so completely that they were suddenly racing against the rising water to rescue wildlife from islands that had not existed before. Kariba demonstrates that danger does not always mean sudden structural failure. A megadam can reshape an entire human and ecological system even when the concrete remains standing. Communities lose ancestral land. Wildlife habitats disappear. River behavior changes downstream. At the same time, millions of people and major industries become dependent on the electricity the dam produces. That creates a complicated legacy. Kariba is both essential infrastructure and a permanent reminder of what large engineering projects can cost. But our number 1 entry shows the most frightening possibility of all. A dam can appear to be operating normally, until machinery weighing hundreds of tons begins tearing itself apart. In Russia, that nightmare became real in 2009. On the morning of August 17, 2009, workers at one of Russia's largest hydroelectric facilities were beginning what should have been another normal day. Then, at approximately 8:13 in the morning, the power station suffered a catastrophic mechanical failure. Within moments, the turbine hall became a disaster zone. Imagine standing inside a hydroelectric plant beneath an enormous dam. Above and around you are turbines, generators, pipes, concrete, steel, and the constant force of moving water. Everything is built on a scale far beyond ordinary machinery. Then something goes wrong. A turbine assembly violently fails. Water begins pouring into the building. Heavy equipment is ripped apart. Generators shut down. The turbine hall floods. Workers have almost nowhere to go. The Sayano-Shushenskaya Dam sits on the Yenisei River in Caucasia, Russia. According to the source, the plant is one of the largest hydroelectric facilities in the country and has a generating capacity of approximately 6.4 gigawatts. Construction began during the Soviet period. The dam rises more than 240 meters and extends over a kilometer. A large percentage of its electricity has historically supported aluminum production in Siberia. On paper, this is an extraordinary engineering achievement, but enormous machines experience enormous forces. Hydroelectric turbines rotate under tremendous loads. Vibration, pressure, wear, and maintenance all matter. According to the source's description of the official accident findings, turbine vibration played a major role in the 2009 failure. The machinery effectively tore itself apart. The accident caused major flooding inside the turbine and generator areas. Power generation stopped. Generators were damaged. Oil was released downstream. Most importantly, 75 people were killed. That is what separates this event from many other entries on this list. There was no need for the entire dam wall to collapse. The catastrophe happened inside the facility responsible for turning water into electricity. The enormous energy normally controlled by the plant became destructive. The source also notes that the plant later returned to operation after extensive repairs. That recovery itself shows the scale of modern engineering. A facility can experience catastrophic failure, be rebuilt, and once again become part of a national power system. Sayano-Shushenskaya matters because it destroys one of the easiest assumptions people make about dams. We tend to imagine only one nightmare scenario. The wall breaks, the reservoir escapes, a flood destroys everything downstream. But a hydroelectric dam is not merely a wall holding back water. It is a complex industrial system. There are turbines, generators, control systems, spillways, structural supports, maintenance procedures, and human beings working inside it. A failure in one major component can become deadly even when the dam itself remains standing. That makes dam safety a continuous process rather than a one-time achievement. The structure may have been completed decades ago, but every inspection, repair, vibration reading, and maintenance decision still matters today. Dams are among the clearest examples of humanity attempting to control forces far larger than ourselves. We stop rivers, store lakes, generate electricity from millions of tons of moving water, and most of the time, the system works exactly as intended. That reliability can make us forget what is actually being controlled. Sayano-Shushenskaya is a reminder. Behind every turbine is water under immense pressure. Behind every reservoir is stored energy. And behind every great engineering achievement is a responsibility that never truly ends. The 9 structures in this video reveal 2 very different sides of the same technology. Dams can provide electricity, drinking water, irrigation, and protection from floods. They can support cities and entire national economies. But when we store enormous quantities of water behind a human-built barrier, risk can never be reduced to zero. Sometimes the threat is extreme weather. Sometimes it is geology. Sometimes it is mechanical failure. And sometimes the greatest cost appears long before anything actually breaks, through displaced communities and transformed ecosystems. Which dam on this list surprised you the most? Tell us in the comments. And if you enjoy factual documentaries about extreme engineering, natural forces, and the world's most extraordinary places, subscribe for more. Because in the next ranking, we are looking at structures so large that they almost seem impossible for humans to have built.